This video describes threaded fasteners and power screws. Threaded fasteners, basically nuts and bolts, are a very common and surprisingly interesting to design form of a non-permanent joint in engineering systems, as opposed to a welded joint which is permanent with bolts or with rivets. You can take the pieces apart and put them back together again. So you've probably seen screws and fasteners in a variety of shapes and sizes. I'm going to scroll down to an appendix at the very back of this document, which has some common and some less common fastener types. The basic hex head bolt, you put it through a couple of plates, you put a hex nut on the end, you need essentially 2 wrenches to tighten it, and you're going to be left with a bolt head that sticks out. There are specialized bolts where the bolt head is not going to stick out, such as this elevator bolt and this countersunk flat cap screw. So that can be a safety issue if people are running their hands along surfaces and you want the cap to be flush. It can also make it easier to fit parts together in close quarters. The lag screw is typically used for wood construction. So there's a number of these. You can look through the applications. The basic hex nut is just a 6-sided internally threaded fastener, whereas the bolts are externally threaded. If you have a lot of vibration in your bolted connection, that can make the bolt and nut come loose. So to stop that, there are various ways of locking the nut. Some nuts have a nylon insert in them, and it creates an interference when you put the nut over the bolt. You have to compress the nylon insert in order to tighten it, so that prevents the nut from coming off easily. There are, in addition to flat washers, there are what we call lock washers. This split lock washer, which has a permanent deformation, and when you tighten it, you end up squashing it so that it all lies in one plane. The desire for that washer to spring back to the shape that's shown basically puts a bit of tension between the bolt and the nut and keeps everything tight. The Belleville washer, it's like a conical spring, and when you tighten the bolt down on it, you're going to squash it. It's going to want to spring back to its original form, and that can maintain the tightness of the connection. So in addition to terminology such as internal and external threads, we need to talk about the standard forms of the thread profile. Okay, there are actually some tolerance grades which you may encounter on bolt and nut thread profiles, and the sloppier the tolerances, the more wiggle room there is between the nut threads and the bolt threads. Typically, screws are right-hand thread, meaning righty-tighty, lefty-loosey. Looking at the head, you turn the head clockwise and it advances forward. Gas fittings for residential natural gas used to be all left-handed threads. So here's some terminology from Shigley Figure 8.1. The major diameter is the diameter you would get if you put a set of calipers across the whole bolt. So you're getting the outside diameter from thread peak to thread peak. Now the smallest possible diameter you could get, if you could go from the root of the thread to a root on the opposite side, would be the minor diameter, or the root diameter. And somewhere in the middle of those you've got a pitch diameter, which is essentially where the load from the nut is assumed to bear on the bolt thread. There's a thread angle. The total included angle here is 2 alpha. And the threads have a crest and a root, and those create stress concentrations, and certain specialized bolts for fatigue resistance will have not quite as sharp a root, because a lot of fatigue failures take place at the first thread root. Okay, the thread angle I mentioned. The lead angle, if you were to unroll a thread and create a ramp, you would get a lead angle, which we can sort of see here as being approximately that angle. That's the lead angle, typically referred to as lambda. So we talked about major diameter, minor diameter, and pitch diameter. The tensile stress area. If you have a piece of threaded rod, you might think it's conservative to assume that the rod has as much strength as, say, the root diameter. So you're basically taking away all the threads in order to figure out how much tensile area you have to withstand yield. Well, I've got a sort of a made-up large thread here. I'll show you. Okay, so if I imagine this to be a thread with a ridiculously high lead angle. Okay, looking right here, here's the root diameter at the top. On the bottom, I've actually got some thread there. Because the thread winds around in a continuous helix, there's actually no part of the screw where you've got entirely root diameter all the way across. So it turns out that the tensile stress area is somewhere between the area you'd get from the root diameter and the major diameter. They did a bunch of experiments, and they found through experimentation that an unthreaded rod with a diameter equal to the average of the pitch and the minor diameters will have the same tensile stress as the actual bolt itself. So when we look at tables of bolt properties, we see nominal major diameter. So let's look at a 5mm bolt. The pitch is the distance between threads as viewed in profile. So there's the pitch P. This is the standard thread profile for the nuts and bolts that you buy at the hardware store. And we can see that the thread angle is 30, so we have 2 times 30 is 60 as the included angle of the V, and the pitch is given. If we have a single thread, then the lead is how far the nut advances if you turn it one rotation. Normally the lead equals the pitch. You turn the nut one turn and you move from one thread to the other. It is possible to have double or triple or other kinds of threads where the lead is equal to 2p, 3p, 4p. And I'll show you one of those in a second. Okay, so the basic thread form for screws and bolts is called the unified national. And there's usually 2 kinds. There's a coarse and a fine. So we've talked about a 5mm bolt. Pitch of 0.8 millimeters. Here's the minor diameter area, which is 12.7 millimeters squared, and here's that tensile stress area I mentioned earlier, which is a bit higher, 14.2 millimeters squared. So that's somewhere in between the minor diameter and the major diameter areas. If I wanted to specify this bolt, I would say it's an M5, M meaning metric, by 0.8. So that will be the pitch. You can see that for the larger sizes, like a 20mm bolt, I can either have a pitch of 2.5 millimeters, or I can have a smaller distance between threads, or a finer thread, with a pitch of 1.5. In the imperial thread system, the threads are specified a little differently. Here's a table for the imperial dimensions. There's a number size until you get up to a 1/4 inch diameter. If I look at a 1/2 inch, if I want to specify a 1/2 inch bolt with a coarse thread, I would first do the diameter, which would be a 1/2. Then I would quote the threads per inch. Okay, so I just found a typo in this table. This is actually supposed to be 13 for a coarse thread. So it should be a 1/2 13 unified national coarse. And if I want to specify a fine thread, then I would specify a 1/2 20 UNF. F for fine. Okay, So you may hear of a quarter 20 thread, quarter-inch diameter, 20 threads per inch, or a quarter 28, which is the fine thread. Once again, we have the areas given. So that's how you talk about bolts to the people in the machine shop. Just to go back for a second to the concept of a double thread. I've got a piece here that came off a lathe, and this looks like an ordinary thread, but watch what happens when I follow one of the threads around. There's a white mark here. Let's see if we can make that a little bit more visible. Okay, there's a white mark here, and I'm going to go around the thread one turn. So I'm going to go around once. So I turned the nut one turn, and I advanced by 2 times the pitch. So that's a double thread. So when they cut these, they just basically take 2 threads and they go parallel all the way around. Now you may ask, why don't they just cut one really ridiculously high angle helix thread? Why not cut just one thread at a really high angle if you want to have your nut move a lot for not a lot of twist? Well, if you only cut threads that are really far apart, in between the threads you'd have this big block of material that would get in the way. So if I cut this thread that goes around like that, I end up having to cut another thread in between so that things don't interfere. This is an EpiPen case, so this is the pens people carry if they're allergic to nuts. And with these things, you want to not waste too much time getting the cap off if you need this thing. So watch this. I'm going to turn this one turn, and it comes off. This is I guess it'd be a sextuple thread. There's actually 6 threads cut side by side, and my lead is 6 times the pitch. Now our root beer bottle, and you may want to get to the contents of that quickly as well, but it's not necessarily life and death. A root beer bottle is, if you look at the threads on the top, there's 3 threads cut. So it's a triple thread on the top of the glass bottle. Now a very particular type of thread that's very useful. Oh, one other thing here. Maybe you've seen bolts with markings on the bolt head. Those markings indicate the grade, the expected strength. So for Imperial, we have the Society of Automotive Engineers specifications. So an SAE grade, 1, 2, 4, 5, 5.2, 7, 8. So it makes as much sense from afar as any other Imperial system of units. But if you look at the markings on the head, you can figure out the grade number, and given the size range, you can find the minimum expected proof strength. Okay. So a proof strength of a grade 5.2 is 85,000 psi. So that means that 99% of fasteners will have at least 85 kpsi of proof strength or more. Now what's proof strength? Well, proof strength is a little bit less than the yield strength. When you work out yield strength using a tensile tester, you do your stress strain curve, you get a linear part. The slope of that's your elastic modulus, and then it starts to do that, and when you get to a strain of a certain percentage, I think it's 0.2%, this value here is your yield strength. But at the yield strength, a little bit of plastic deformation has already occurred. If you go back to the point where you haven't begun that deformation yet, the point where if you relax the load it'll go all the way back to 0 with no offset, that is your proof strength. And that's what's used in bolted joint design. For metric bolts, they refer to a class instead of a grade. Okay, I can find it here. Metric mechanical property classes for steel bolts, screws, and studs. Here they have a decimal number, they stamp it right on the bolt head, and we have a minimum proof strength now in MPa. Yield strength is given as well as the minimum tensile strength, that's the ultimate strength basically. Okay, so now we know how to talk about screw threads. Let's talk about power screws. You may have referred to these as lead screws or linear actuators. These have a tremendous mechanical advantage, and the goal is to convert rotary to linear motion. We can transmit very large loads. We can lift very heavy things with a small input torque. C-clamps, a screw-type jack for jacking up your car. The Instron machine, which does all these tensile tests, it has a lead screw, and it turns that into a very slow elongation, which can obviously rip steel apart. Sometimes you don't need to lift a large load, but you need to position something precisely. So if you need to move a lathe chuck a very small amount, it's more precise if you can turn the crank 7 or 8 times to get a few millimeters of advancement of your bit or your chuck. So lead screws, power screws are good for that. Here's a couple of different ways of configuring these things. So here the black is the screw, and you would turn a handle and the screw would slide relative to some internal threads in this base, and you would raise the load. What would happen is the top part here would slide relative to this portion that's joined to the weight. There's a little ball bearing shown there. It's also possible to turn the nut, and then the nut would slide on the base, and you would lift the lead screw. And here you can turn the nut, and the nut will actually ride up the screw. And once again, we have what's called a collar, this area where there's going to be sliding or rolling if you use a ball bearing. Okay, so there's a load to be lifted. There's a rotating element to which you're going to apply an input torque, and you're going to lift a certain amount of weight. All right. Now you don't use the same type of threads for power screws that you use for nuts and bolts. It's a much more rugged looking thread. The oldest type of power screw thread was called the Acme thread. It had a thread angle of 14.5 degrees, so we have 2 alpha is 29 degrees. And the distance between threads, if we go up as high as what's called the mean diameter, then we have a distance of p over 2 across a thread, and then p over 2 to the next thread. So the mean diameter, or the pitch diameter, is where those two widths are equal. People realize that if we use stubbier Acme threads, they might be a little bit easier to heat treat. You can get your heat treatment down through a lower height. Square threads are sometimes used. They're more efficient, but they're harder to make. And you can also get these buttress threads, which are sort of an asymmetrical form of the Acme thread, and these can take a tremendous amount of load in one direction, more so than the other. On the next page we can see some tables of power screw thread properties. This one's from a classic textbook by Juvenal. So given the major diameter, you can pick off the number of threads per inch, which will be 1 over the pitch, for Acme and Acme stub, also for square and buttress threads. And then from yet another textbook by Norton, there's a fairly complete table of Acme thread dimensions. So major diameter in inches, threads per inch, thread pitch, pitch diameter, minor diameter, and tensile stress area.